Now we discuss the applications of residue calculus. So that is the evaluation of real definite integrals. Many important definite integrals can be evaluated by applying the residue theorem to properly chosen integrals. So here the contours chosen will consist of straight lines and circular arcs. So there are many integrals whose evaluation by conventional methods is extremely difficult, and in some cases the evaluation of the integrals is impossible too. But by using complex analysis, and that means by using residue theorem, those integrals can be easily evaluated. So this method of calculating the integrals using residue theorem saves one from the complicated mathematical calculations. So complicated mathematical calculations ഒന്നും ഇല്ലാത്ത തന്നെ complicated integrals നമുക്ക് residue theorem വെച്ചിട്ട് integrate ചെയ്യാൻ പറ്റും. Here in this module we discuss the evaluation of integrals by 5 different methods. So first one is the integration around a unit circle. Here integrals of the type integral 0 to 2 pi f of cos theta sin theta d theta, where the integrand is a finite and a rational function of sin theta and cos theta, can be easily evaluated by considering a circular contour of unit radius. So we know that for a complex variable z equal to r e to the power I theta. So when the radius is 1, z equal to e to the power I theta. So for the integrals of this form, for the integrand is a function of cos theta and sin theta, and the limits of the integration is from 0 to 2 pi, can be evaluated by using a unit circle. So for a unit circle, z is equal to e to the power I theta, r equal to 1, z equal to e to the power I theta. So we know that cos theta is written as e to the power I theta plus e to the power minus I theta divided by 2. So z equal to e to the power I theta, then z star is equal to e to the power minus I theta. So this cos theta can be written as z plus z star by 2. And similarly, we can write sin theta as e to the power I theta minus e to the power minus I theta by 2i. So that is z minus z star by 2. But here r is 1, and we know that z star is equal to e to the power minus I theta, can be also written as 1 over e to the power I theta. So that is 1 over z. So z star is 1 over z. So therefore cos theta can be written as z plus 1 by z divided by 2, or 1 over 2 into z plus 1 over z. And similarly, sin theta can be written as 1 over 2i z minus this is 2 1 over z. So, and the integration is around a unit circle, a circle having radius 1. So here it means 1, here it means minus 1, I minus I, and the center is 0, 0. Okay, so the integration takes the form. So when we convert thetas in terms of z, the integration takes the form closed integral f of z dz over c, where c is a unit circle mod z equal to 1. Initially തന്നിരിക്കുന്ന സർക്കിളിൽ ഇന്റഗ്രന്റ് എന്ന് പറയുന്നത് കോസ് തീറ്റയുടെയും സൈൻ തീറ്റയുടെയും ടേംസിലാണ് തന്നിരിക്കുന്നത്. We have converted this in terms of z. cos theta z ന്റെയും 1 over z ന്റെയും ടേംസിൽ എഴുതാം, sin theta അങ്ങനെ എഴുതാം. So we get f as a function of z. അപ്പോൾ ഇന്റഗ്രൽ 0 to 2 എന്ന് പറയുമ്പോൾ ഈ കംപ്ലീറ്റ് ക്ലോസ്ഡ് സർക്കിൾ ആണ്, യൂണിറ്റ് സർക്കിൾ ആണ്. So this can be written as closed integral f of z dz, and over the contour is a circle having radius 1 mod z equal to 1. അപ്പോൾ ഈ ഫോമിലാക്കി കഴിഞ്ഞാൽ നമുക്ക് റെസിഡ്യൂ തിയറം അപ്ലൈ ചെയ്യാം. ഇതിലെ സിംഗുലാരിറ്റീസ് കാണാം. സിംഗുലാരിറ്റീസിലെ റെസിഡ്യൂ കണ്ടു കഴിഞ്ഞാൽ ക്ലോസ്ഡ് ഇന്റഗ്രൽ f of z dz is equal to 2 pi I times the sum of residues of f of z at poles inside the contour C, where C is a circle of unit radius with center at origin. So this method becomes more clear when we do one problem. So the question is that show that I is equal to integral 0 to 2 pi cos 2 theta d theta divided by 1 over 2a cos theta plus a square is equal to 2 pi a square divided by 1 minus a square, provided a square is less than 1. First of all, we consider a unit circle. A unit circle means a circle having radius 1. So for that, z equal to e to the power I theta, and mod z is equal to 1. Dz by d theta is I e to the power I theta. So dz is equal to I e to the power I theta d theta. Okay, and therefore d theta is equal to dz divided by I e to the power I theta, but I e to the power I theta is iz, dz by I z. 1 over I is minus I, so minus I dz by z. So we have to replace d theta by minus I dz by z, and cos theta and sin theta in terms of z and 1 over z. So we know that cos theta is equal to 1 by 2 into z plus 1 by z. So cos 2 theta, so which can be written as 1 over 2 into e to the power I 2 theta plus e to the power minus I 2 theta. So that is 1 over 2 e to the power I theta square plus e to the power minus I theta square. അപ്പോൾ e to the power I theta z ആണ്, 1 over 2 z square, e to the power minus I theta is 1 by z whole square, that is 1 over z square. So substituting these values of cos theta and cos 2 theta in the above integral, we get 1 by 2 here can be taken outside, closed integral z square plus 1 over z square into d theta is I dz by minus I dz by z divided by 1 minus 2a cos theta is 1 by 2 into z plus 1 by z plus a square. And now by taking I outside, we have minus I by 2 closed integral. Z square is taken as a common factor, z to the power 4 plus 1 by z square into dz by z whole divided by 1 minus 2 and 2 cancels, a into here z is taken as a common factor, so z square plus 1 divided by z plus a square. Okay, so here you can take z as a common factor, and we get minus I by 2 closed integral z to the power 4 plus 1. Here you have z, so dz by z here, sorry, z square into z is z cube, and here z is a common factor, z minus a z square plus 1 plus a square z all divided by z. So here z and z here cancel. So this division is converted as multiplication with reciprocal. So we get like this, and here we expand this z minus a z square minus a plus a square z. So we get like this, and we can simplify this by taking z as a common factor. So we get z into 1 minus a z. So here also we can take a as a common factor, minus a into 1 minus az. So 1 minus az is a common factor, 1 minus az into z minus a. So this term can be written like this, and therefore we get minus I by 2 closed integral z raised to 4 plus 1 by z square, and this is written as z minus a into 1 minus az dz. Okay. Now this is written as closed integral f of z dz over c, where c is the contour, mod z equal to 1. So here the unit circle is the contour, and f of z is the function which is given by f of z is equal to minus I by 2 z raised to 4 plus 1 divided by z square into z minus a into 1 minus az. So now we have to find the poles of this function, and the poles of the function are given by when the denominator equal to 0, z square z minus a into 1 minus az. So this z minus 0 whole square. So the root z equal to 0 repeats, so we can say that f of z has a double pole at z equal to 0. So other poles are z minus a equal to 0, that is z equal to a, and the other one is 1 minus a z equal to 0, that is a z equal to 1, and z equal to 1 over a. But in the question it is given that a square is less than 1. So that means a has a value between minus 1 and plus 1. A square is less than 1. So root is a is having a value between minus 1 and plus 1. So modulus of 1 over a. So a is less than 1. 1 divided by a quantity less than 1 is greater than 1. അപ്പോൾ നമ്മൾ യൂണിറ്റ് സർക്കിൾ ആണ് ഇത് ഇന്റഗ്രേറ്റ് ചെയ്യുന്നത്. So when we mark the unit circle, we can see that z equal to 0 is a point inside the contour. A somewhere here is a point inside the contour. A is less than 1, but 1 over a is greater than 1. So we have to calculate the residues at z equal to 0 and z equal to a only. We don't have to calculate the residue at 1 over a to calculate the integral. And so this is the unit circle, mod z equal to 1. So since this is a unit circle, 1 over a is outside. So we know that now closed integral f of z dz is nothing but 2 pi I into sum of residues, all residues which are inside the contour. So we have to find out the residues at z equal to 0 and z equal to a. Z equal to a is a simple pole, so we can find the residue or residue of f of z at z equal to a as limit z tends to a, z minus a into f of z. Okay, so this is how we calculate the residue for a simple pole. So substituting f of z over here, we get limit z tends to a z minus a into minus I by 2 z raised to 4 plus 1 divided by z square into z minus a into 1 minus az. Z minus a and z minus a cancels, and we will get this. Applying the limit z tends to a, we get minus I by 2, z goes to a to the power 4 plus 1 divided by a square into 1 minus a into a, 1 minus a square. So this is the residue of the function at z equal to a. So now we have to find out the residue at z equal to 0. Z equal to 0 is a double pole. The residue of f of z at z equal to 0 as a double pole can be calculated as limit z goes to 0 d by dz of z minus 0 whole square into f of z. So substituting the value of f of z, we get limit z goes to z0 d by dz of z minus 0 square is z square into minus I by 2 z raised to 4 plus 1 z square into z minus a into 1 minus az. Okay, so this z square got cancelled and I by 2 can be taken outside. So this is limit z goes to 0 minus I by 2 d by dz of z to the power 4 plus 1. So for the easiness of the differentiation, we can multiply those two terms to get z minus az square, then minus a minus plus a square z. Okay, so the derivative of some fraction. We know how to calculate the derivative of a fraction, that is the denominator into the derivative of numerator. The derivative of z to the power 4 plus 1. 4 z cube minus the numerator into derivative of denominator. Derivative of denominator is 1 minus 2az plus a square. Okay, divided by denominator square. Z minus a z square minus a plus a square z whole square. So now we apply the limit. Okay, so applying the limit as z goes to 0, this term will be 0. 4z cube is a common factor here. So when z equal to 0, this term vanishes. So we have minus I by 2 into 0 minus z raised to 4 plus 1. That is 0 plus 1. 1 into 1 minus 2az plus a square. So this term becomes 0. 1 plus a square divided by z will be 0, this will be 0, this will be 0. So minus a whole square. So that is equal to minus will be plus I by 2 into 1 plus a square by a square. So this is the residue of f of z at z equal to 0, which is a double pole. So we have found the residues of the function f of z is equal to minus I by 2 z to the power 4 plus 1 z square into z minus a into 1 minus az at z equal to 0 and z equal to a. So z equal to 1 over a is the point outside the door, and therefore we don't have to calculate the residue at this point in order to calculate the integral, closed integral f of z dz over c, where c is a unit circle. So mod z equal to 1. So a is here, 0 is here, and 1 over z is outside. So closed integral f of z dz is equal to the 2 pi I into the sum of all residues. So this is nothing but our LHS. Our LHS integral 0 to 2 pi. This function cos 2 theta d theta by 1 minus 2a cos theta plus a square is written as in this form, closed integral f of z dz, where f of z is this. So this is equal to 2 pi I into sum of all residues within the contour. That is residue of the function at z equal to a and residue of the function at z equal to 0. So we have calculated those two residues and we just substitute, and we get 2 pi I into at z equal to a, the residue is minus I by 2, a to the power 4 plus 1 divided by a square into 1 minus a square. And at z equal to 0, the residue is I by 2 into 1 plus a square by a square. So here in both this I by 2 is a common factor, I by 2 a square is a common factor. So we can write it as 2 pi I into I by 2 a square. Or we can take minus I outside, minus I by 2 a square into a to the power 4 plus 1 by 1 minus a square minus. So we have taken minus I by 2 here. 1 plus a square. So we can take 1 minus a square as a common factor here. So we get 2 pi into I square is minus 1, minus minus is plus. So this is plus 1, 2 pi by 2a square. So 2 cancels, and we have pi by a square into a to the power 4 plus 1 into 1 minus a square minus 1 plus a square into 1 minus a square by 1 minus a square. Okay, it's a common factor now. So we have pi by a square into a to the power 4 plus 1 minus a plus b into a minus b is a square minus b square. So that is 1 minus a square whole square. That is a to the power 4 divided by 1 minus a square. So we have this 1 and minus 1 cancels, pi by a square into a raised to 4 plus a raised to 4, 2a to the power 4 into 1 minus a square. So here this 4 and this 2 cancels, and there will be 2 here. 2 pi a square by 1 minus a square. So this is nothing but the RHS. So we have proved that LHS is equal to RHS. That is, we have shown that integral 0 to 2 pi cos 2 theta d theta divided by 1 minus 2a cos theta plus a square is equal to 2 pi a square divided by 1 minus a square, provided a square is less than 1. So we have seen that any integrals from 0 to 2 pi or integral 0 to pi. Pi ആകുമ്പോൾ നമ്മളൊരു 1/2 എടുക്കണമെന്നേ ഉള്ളൂ. Where the function, the integrand is a function of cos theta and sin theta, can be integrated by using a unit circle z equal to e to the power I theta. So first we convert these integrals as a function of z by substituting cos theta as 1/2 z plus 1 by z and sin theta as 1/2 I z minus 1 by z. And cos 2 theta, sin 2 theta, etc. can be converted in terms of z square, etc. and 1 by z square, etc. And we get a function of f of z, and find the poles of this function and mark the poles which are inside a circle of radius 1, inside a unit circle, and find the residues. Then 2 pi I into the sum of these residues gives the integral. So this is an easy method for finding the integrals of this form, integral 0 to 2 pi, and the integrand is a rational and finite function of sine theta and cos theta. So this integrand can be easily evaluated by considering a circular contour of unit radius, and by making the substitution z equal to e to the power I theta. So now you have some assignment questions. Calculate integrals of this one. First one is evaluate the integral 0 to 2 pi d theta divided by 5 plus 3 sine theta. And the second question is evaluate integral 0 to pi. So remember that the integration is from 0 to pi. So you have to consider that I equal to integral 0 to 2 pi, and finally the result is nothing but I by 2. Okay. Sine square 0 to 2 pi ആയാലും അതിനെ ക്ലോസ്ഡ് ഇന്റഗ്രൽ ആയിട്ട് പറയാൻ പറ്റും. ഇപ്പോൾ 0 to 2 pi ചെയ്തിട്ട് I by 2 ചെയ്യണം. So the question is integral 0 to pi sine square theta d theta by 5 minus 4 cos theta. Third one, integral 0 to 2 pi cos 3 theta divided by 5 minus 4 cos theta d theta. Okay, so please do this problems as an assignment. So what you have to do is that first write d theta in terms of dz. We know that d theta is equal to minus I into dz by z, and sin theta can be converted as 1 over 2 pi I z minus 1 over z. So please do this, and similarly you can do this sin theta is this, and you can find sin square theta by squaring this. And also you can find cos 3 theta as e to the power I 3 theta plus e to the power minus I 3 theta by 2. So that is e to the power I theta cube z cube minus 1 over z cube into 1 by 2. So you can do this problem also. So these are the assignments for you. Okay, thank you.